So we're going to talk a little bit about FastAPI and friends and stuff. Sentry is organizing this event, so thank you very much, Sentry. If you haven't checked them out, go check them out. We're going to start with just a little bit about FastAPI. Now, for those of you that don't know, FastAPI is a web API framework. This is what you will use to create APIs, to create the thing that runs on the server. And web means that it's just like JSON. So JSON going through HTTP. This is what you will use to communicate with your browser, with mobile apps, with desktop apps, or other services, things like that. That's what you will use FastAPI for. So FastAPI, the idea with FastAPI is that it's easy and short. So you just import from FastAPI, you import the FastAPI class. Then you can create an instance of this class, and then we can use this decorator with this @ symbol. This is the way that we are telling FastAPI, hey, do the thing that you do with this that is below that. We do that with this @ symbol. What we are telling FastAPI here is whenever someone goes to the root path, so just a slash, sending an HTTP GET request, then this is the function that should handle that. And you can use an async function because oh, we have music now. Cool. Yeah, now I can rap. Cool, nice. So we can use async because FastAPI is underneath an async framework, but you can also use normal and regular def functions. This is what you will normally do. And we are just returning a dictionary. FastAPI will make sure to convert this to JSON automatically. So you write some basic code, and like the more FastAPI code you write is the less code API you have to write. So you can focus on the business logic of your application. That's the idea. Although, yeah, I guess like most of you already know that, but yeah, anyway. This is a bit more complex application. We have this path that has a path parameter in curly braces. This is the same syntax that you will use for F strings. We just don't have the F here. But the idea is that it will be easy to remember because it's the same curly braces. And then FastAPI will extract this from the URL after /items/. So it's going to take this 5 and it's going to put it inside of this parameter. And because we are telling FastAPI, hey, this is supposed to be an integer, FastAPI will make sure that it is actually an integer. And you can see this comes from the URL, so this is natively or naturally, this is a text, this is a string. But FastAPI will make sure to convert it to an actual integer so that what you have in your code is exactly what you define that you expected. We're also saying, hey, we also have this parameter q, this is a string, by default this is none, because it's not in the path parameters, FastAPI will know that it has to extract it from the query parameters, which are these that go after the question mark. So this value, some query is going to go in this parameter q. And because this has a default value, this is not required. Then, if we go to /docs, we have automatic API documentation for this API that we created. And we have the item ID that is defined here. This is an integer, goes in the path, and this is required. And we also have the Q parameter, which is a query string parameter. So we have these automatic API docs by default, just by using these standard type annotations. And you just write some basic code, and then good guy FastAPI writes a docs user interface for you. That is the idea. Now let's say that we want to be able to receive a body in this handler. So FastAPI is built on top of 2 libraries. Starlette does all the web parts, and Pydantic, this one, does all the data parts. So we are going to import from Pydantic, we import the base model, and then we create a class that inherits from this base model. And then we define the shape of the data with the same standard type annotations. So we are saying, hey, name is going to be a string. And ingredients is going to be a list of strings that by default is just an empty list. Name doesn't have a default, so this is required. Ingredients has a default, so this is not required. And then we just define that in the same parameters. We are saying, hey, food is going to be an instance of this class, food. And now this is going to be a post request because we want to be able to receive a JSON payload, so it has to be a post method or a post operation. And because FastAPI makes sure that we receive an actual instance of this class, then we can access these attributes and all that stuff. And then if we go to the docs, now we have automatic docs for the shapes of the data that we define. This is not the shapes that come with FastAPI. This is the data that we are defining in our code for the things that are important for our code and for our things. So you can see that now we have name is a string and ingredients is a list of strings or like a JSON array of strings. And we can actually try it out. So this is running in the browser, but you can interact with the running code that we are developing right while we are developing. We can interact with it through the browser. So we can send, hey, I want to send an item. This is an empanada that has some ingredients. And then we can execute this, and then we can receive the message here from the code that is running there live. So this can help a lot iterating quickly the development of the API. And you can be happy like this cat sending empanadas in requests. Now let's say that we want to have a body and a query. So we just add parameters to the function. So food is an instance of the class food. Delivery is going to be a Boolean that by default is false. It has a default, so this is not required, and it's going to be, FastAPI will make sure that this is actually a Boolean. And because it knows that it's a Boolean, this is how we will use it. We will send it in the query parameters, but because the UI and everything knows that this is a Boolean, then we can have this user interface that can show us like, hey, these are just the only two options, so you can just like choose from that. So we can have very nice documentation automatically generated from our code. So you don't have to put everything in a body, you can put stuff in query parameters. Now, if you want to have a JSON array of JSON objects, or like a Python list with Python dictionaries will be equivalent, you just use, again, standard type annotations. Now, instead of one single food item, we're gonna have a list of instances of food. And then, we just use the code using the types that we defined that we expected to receive. And if we check the automatic API documentation, we can see that now this is a JSON array of JSON objects, or like the equivalent in Python will be a list of dictionaries with the shapes that we defined. So if you want to have JSON inside of JSON, you can just do that. You can have arbitrarily complex nested data structures that are just defined with the standard Python type annotations. So you define the shape of the data that you expect to receive with standard type annotations, and then like FastAPI will extract the information and will do the rest. What happens if you send invalid data? So this is valid JSON. It's not that there's like an extra comma here or something. So as JSON is valid, but the data is not valid with the shapes that we defined that we expected to receive. So let's see how this is invalid. So the first item, this has a name, this is a string, it has ingredients, this is a list of strings, so this is all good. The second item has a name, this is a string. This one doesn't have ingredients, but ingredients had a default value, so they are not required. The next item has the name, this is a string, this is fine. Then ingredients is a list, this is fine. The first ingredient is salt, this is fine. But the second ingredient, this is actually a sneaky object, so this is not a string. So this is not valid. And notice that the thing that is invalid here is actually deeply nested inside of this data structure. It's inside of a list, inside of an object, or like a dictionary, inside of another list. And still like, well, it's invalid at that point. Then we have this other item here that has a food name. This one doesn't have a name. We say that name was required, but this doesn't have name, this just has food name. And if we execute this query, FastAPI will tell us that, hey, there's a problem with the data that you are sending. It's gonna do validation of the data automatically. And it's not just gonna tell us or tell the client, hey, your data is invalid. It's gonna tell the client exactly where and how the data is invalid. So we can see that in the body, in the orders, at the index 2, so the third item, inside of ingredients at index 1, so the second item, a string type was expected, and we actually sent a sneaky object. And we also get the next error saying like, hey, inside of the body in orders at index 3, the name was a field required, and we actually sent a food name. So we are getting like all the information to be able to actually fix the data as well. We're getting not just like, hey, you have an error in your data, and we are not just protecting our code from that invalid data. We're also telling the client, this is exactly how you are messing up. So then, without valid data, FastAPI will protect our code from executing with invalid state and like crashing servers and getting calls at 2 a.m. In the morning because something is wrong in the servers. But when the data is valid, FastAPI will just let your code run exactly as you defined that you expected it to run. And then, because this is all based on standard Python type annotations, you get the features that you will get from type annotations independent of FastAPI. Like you will get auto-completion everywhere in your code. So for example, here, we are just defining type annotations in this class, and then in this parameter. And because of that, the editor knows that, okay, orders is a list of food instances, then we can iterate for each one of the food items inside of orders, and each food item is gonna have an ingredients list, and this list of ingredients, each ingredient is gonna be a string. So it knows that at this point, when we try to trigger auto-completion, this is a double nested for loop. And still, it knows that if we try to trigger auto-completion for ingredient, these are the methods for a string. It knows the type of this. So the editor can help you a lot with all this auto-completion. And you can be happy, like this guy. This is how I code when I have auto-completion in my editor. because I have really bad memory. I need auto-completion. That's why I made FastAPI. Now, you also have inside, in the same double nested for loop, or like whatever is the complex data structure, or like whatever is the complex code that you have inline errors in that telling you whenever you are doing things that are broken with types. So if you try to sum an ingredient, which is a string, with an integer, you get the errors right there in the editor before you commit anything to Git. So you can save yourself from a lot of bugs, and then you can say like you never made those bugs, and then you can claim that you're a 10x engineer or something like that. And this is all based on standard Python types. So you don't have to import custom string from FastAPI or something like that. You just use the standard Python type annotations, and you get all those things. So FastAPI is based on standards, like OpenAPI, which uses JSON schema and OAuth 2. This is what you use for, I don't know, login with Google or login with GitHub or things like that. So you can use those single sign-on systems, or you could build a single sign-on server with FastAPI. All this is part of these standards. So by using standard code, you get something that is based on standards automatically. And by using standard type hints, you get all the features that you will get normally, like auto-completion and inline errors. But on top of that, FastAPI adds data conversion, data validation, and like, data documentation on top of that. And, this is just standards for free. You don't have to do anything else to get this out of the box. Now about performance. This is a benchmark run by a third party. They benchmark a bunch of different languages with a bunch of different frameworks. I'm showing you only the ones for Golang and for Python. So Go is a compiled language. It has to be faster. It has to be faster. Nevertheless, for this particular benchmark, FastAPI and a bunch of others here get to be, like sort of on the ballpark of the best that you can get with Python. And in some cases, in this particular benchmark, they get to be a little bit faster than some of these Go frameworks. So this is quite nice for being able to stay in the Python ecosystem and using like all the Python libraries and still getting quite decent performance. And in this case, this benchmark was running like 15,000 requests per second, which is over 9,000 requests. So it's fine. You can be happy about that. Now, FastAPI has a bunch of other features like dependency injection, a bunch of security and OAuth utilities, WebSockets, files, background tasks, easy graphical integration, templates, like a bunch of all the things that you will expect from one of these frameworks. But yeah, that's like a short introduction of FastAPI for those that didn't know. Now, a bit of the current state of FastAPI. So a bit of the stats and like the growth and how these things are going and are happening. So the GitHub stars have been like growing a lot. It has like 60,000 something GitHub stars. It's been growing like for around like 1,000 stars per month. It's like, like even approaching the giants that are Django and Flask. I never expected that. I always thought that FastAPI was going to be like one of these hipster frameworks that 50 people around the globe use and say like, this is the best, and no one knows what they are talking about. That was what I was expecting. And that was like the biggest hope, that it was not just me, that it will be like 50 others. But it seems like there's more people also using it. And if you just add Ruby on Rails, for example, to this graph, you can see that in general, it's just cool to be in Python because it's just like growing and it's just like working quite nicely. And yeah, like I never expected that. It has a bunch of downloads. Like now it has like 20 million downloads per month, which is very cool and very scary at the same time. In the latest Python developer survey, at least the released ones, it was the one with the fastest growth, and it's currently the only one growing from the ones that they were comparing, so that's cool, I guess. Also in the Stack Overflow developer survey, at first it was like, between Symfony, Svelte, Gatsby, I don't know, and then it just passed some of these, passed Ruby on Rails, now it just passed AngularJS, so it's been gaining some adoption, and I think that's cool. And scary, but cool. So FastAPI stonks, nice. Like it's got like some other like awards or stuff, like ThoughtWorks Technology Radar said like it was something that the enterprise should start trying out or considering or whatever, like, those terms they use. StackShare called it the #1 developer tool of the year over GitHub Copilot. I don't know why, but still, thank you, nice. Like, and some other people have been saying like, oh yeah, FastAPI is cool enough to try it out. Now, a little bit about who uses FastAPI. Like, what are the companies like? There's a bunch of companies. You might recognize one or two of those that are using FastAPI. It's also used for things like the web space, the Space Telescope Institute of the United States that were handling the data from the Webb Space Telescope that took these pictures. So the scientific data that we're serving for, like, around the world with all the scientific data was done with FastAPI. Also, like, OpenAI uses it for the ChatGPT stuff, like the documentation. The default example for building ChatGPT plugins is with FastAPI. They also have like their own plugin thingies with FastAPI, and ChatGPT is like the fad now, so they go that slide. It's also used for simulating galaxies, and this resulted in like being able to observe the first quasar with the Webb Space Telescope. I have no idea what that means, but it sounds so cool. Like, yes, a quasar, like, sure, nice. And when I was checking that, I realized that it's used at the CERN to control the particle accelerators, like the Large Hadron Collider. They have a bunch of FastAPI services to control those things. So if at some point you see that there's like, some black hole forming in Switzerland and like hitting the whole planet, file an issue in FastAPI. It might be my fault. I hope not. This is really scary. And when I showed this, like, someone also commented, like, oh, we are also using it for the, what is it, the large, very large telescope and the extremely large telescope, which are the largest telescopes on the planet, and we are using it for controlling that, and it's like, oh, another scary thing. They're also using it for controlling single atoms for quantum computers and things like that. Another guy told me right after posting all this, but like, yeah, didn't have enough time to put more slides. But yeah, like, I don't know, the people are using it for very cool stuff, which is like super exciting. The next generation of Jupyter server is also going to be using FastAPI, which is called Jupyverse, that powers Jupyter Hub. So that's very cool as well. So yeah, it's like a bunch of cool usages of FastAPI that I never expected will happen. So that's super nice. Thank you. Now a little bit about FastAPI, Pydantic, type annotations in Python, because Python and type annotations have been growing in the Python ecosystem. And it's like very exciting because there's a lot of, and like I have one of the main people like doing these things happen looking at me like, now I'm nervous. I'm not gonna say anything wrong, I hope. So, like, I personally feel that Python is a great language, and like the way that this is growing, there are growing pains, but at the same time, we're being able to grow in the directions that point to the things that we actually need to do. And right now, type annotations were designed, like the original design was to be able to check that your code was correct, and that was it. The same thing that you will do with TypeScript, just like, oh yeah, the code is correct, now just run it. But Python has this particular ability that almost no other language has, that is being able to extract the information from these types at runtime. And these are the tricks that we are doing in FastAPI, Pydantic, and all these tools. And now, using these things at runtime are like a first-class citizens. You can see, like, Pablo Galindo Salgado, Carol Willing, like the people that decide the future of Python, or Łukasz that came here from Poland, which is like, so cool. This is something that is considered first class in Python. It's something that is considered like, like they are paying a lot of attention to us, to the Python community doing runtime types, like FastAPI, Pydantic, and all that stuff. Like this means all of you. So you are very important for Python in general. We also have typing extensions that allow us to try out a bunch of experimental and new things, even in previous versions of Python. We also have things like the PEP 649 that was designed. It was just a shit ton of work. Oh, sorry, I don't know if I can say those words, but yeah, anyway, still, it was a shit ton of work done by like a very smart people, including like, Larry Hastings and like Carl Mayer, like, very, very smart people, very smart engineers at Meta, things like that, just putting a lot of effort into making sure that we can keep doing these things in the best way possible. And like one of the main use cases for this are Pydantic, FastAPI, TARP, and these things. So like it's, Python is taking very seriously these use cases, and it's like great because we can like grow all together in a very nice environment. We also have annotated that we can use for very cool things. If you check the FastAPI docs or Typer docs, now everything is using annotated. We also have data class transform that is, it was made to help and support things like Atters, that we have here, or Pydantic, and a bunch of other tools that use these type annotations and use this information in smart ways that are a little bit beyond just checking that the type is correct. So, like, I think it's a very nice time where we have like all the tools and all the developers and all the ecosystem and the people that are making Python itself being able to just like work together and just like, continue engaging and creating this ecosystem and just like running very happily, like the Tele2 developers or whatever. Now, a little bit about the recent features of FastAPI. These are some things that you might have seen or might have not seen, because I'm just showing you things from this year, not even like previous years, or like last year or something. For example, now you can define the response model in type annotations. So now you can say, this thing is returning an item, an instance of the class item. You can do it in the type annotations, and FastAPI will extract this information for doing the data validation, serialization, also data filtering. So if you say, I'm going to return a user, you can return an object that contains the password, but FastAPI will make sure that it doesn't contain the password if the shape of the data that you define doesn't contain it. So you can do like all these things just with these type annotations. The documentation is generated automatically, the standards, all the stuff, just based in the standard return type annotations. Now there's support for the lifespan events, which replace the start and shutdown events. So you can, instead of having independent functions to handle that and having to handle state independently, you can have this function that will have a yield in the middle, and then you can do things like having state that is shared, that is created before the app starts, and that you can use that same state when the app finishes without having to have global variables or things like that. I want to improve the API of this a bit and like how you interact with it in FastAPI, but still, we can use it right away. There's also support for annotate, and it's also the recommended way to do things now. So types are now more correct, and there's better interoperability with the tools and the things that you can use. For example, you can use, if you use annotated, you could use the same function for FastAPI and for Typer in the same code, and you will be able to use that same function for handling a request or a command line application. The same way, if you were calling this function before, because we have all this additional metadata inside of annotated. This is what this means. Before you will have query, this query thing will be in this side, in the default value of this parameter. That will mean that FastAPI will make it work. It will handle like everything, and it still is supported. It still is handled, and it will be supported. But the thing is, if you were going to execute this function yourself directly, instead of letting FastAPI handle it because you wanted to execute that function in some other place of the code, then the default value of Q will be some strange object query something something. Now, having this in annotated, it means that if you call the function in some other place, it's going to indeed have the default value of none. But if you call it through FastAPI, then FastAPI will do the additional stuff of making sure that, yeah, this has a default value of none, so it's not required, but it also has to be extracted from the query, and it has a max length of 50. So now you can reuse this code much more easily because we have support for annotated. The same with Typer. That also supports and recommends annotated. There's a bunch of other features like dependencies in WebSockets that also have like some things to be improved, but now there's support for that. A bunch of performance improvements, a bunch of bug fixes. The new big features are Pydantic version 2, which was rewritten in Rust, and we're gonna hear a bunch about that from Samuel himself. We also have like support for OpenAPI 3.1.0, which is the latest version. This is compatible and based on the latest JSON schema, which means that you just have the latest versions of the standards, which is the the more compatible of the things that you could do. You can have like better automatically generated clients and SDKs and things like that. We also have like more correctness with types just because of Pydantic v2, because things are just more exact, and also a lot more performance just because the internals are written in Rust. So we get a bunch of FastAPI features. Now, some of the future plans for FastAPI. This is one of the things that people ask me the most, and this is important. This is non-binding, but still, I'm gonna share. So this has to stay between us. The future plans for FastAPI. Yeah, I don't know. No, I actually do know what are the future plans. Don't look so scared. So some of the things, we're going to have a code reference or like API reference, so the documentation will show Hinek is looking happily and not, he's holding the complaint that he was going to show afterwards. So we're going to be able to go to the docs and see what are all the optional, all the parameters that we can have for functions, all the classes, all the things that you can use. Because right now there's a long tutorial explaining how to do all the things, and like the tutorial is made to teach you how to do things, but once you know how to do all that, and you just want to come back to the reference and say like, what are the options for this parameter, what is this for, and like just quickly check that, we're gonna have that. This is gonna come for FastAPI, Typer, SQL model, asyncer. Like this is the thing that I have been working the most recently, and it also involves that we're gonna have new ways and tools to document these things. And it will also, the way that I'm doing it will also help me and like allow me to test that the doc strings are consistent along like all the functions, and like there's just, you know, just a lot of work being done through this. But this new way and this new system is also already supported by make doc strings. So, you know, like this is just gonna work, and it's gonna be quite cool, I think. Some of the other feature plans, because SQL model is quite connected to FastAPI. It was made for FastAPI and is based on Pydantic just to be able to use it with FastAPI. FastAPI doesn't depend on SQL model doesn't depend on FastAPI, but it's just made to be very easily integrated. So it's gonna have support for SQL Alchemy 2, Pydantic 2. It's gonna have like async tools and docs. Like actually there's a bunch of code that is already there and that you can already use, but it's not in the docs yet. There's gonna have like integrated migrations, again using Alembic, which is the tool that you will use for SQL Alchemy, but it's just gonna be integrated into the code for SQL model, and also like a CLI for running the migrations built with Typer, which means that you will have auto-completion in the shell, in the terminal, when you're trying to run the migrations and things like that. Also, the SQL docs for FastAPI are going to use SQL model. Now for Typer, we're going to have optional async support with NEIO. So if you want to use async functions in Typer, you're going to be able to do that, installing the additional NEIO package, but you know that this is just a pip install Typer standard or something like that. It's also going to have, like this is on the plans, to have optional Pydantic support so that you can define more complex data shapes in your CLIs, and it's going to be parsed by Pydantic. And for async, we're going to have like the latest NEIO, and FastAPI, the concurrency docs, and like explaining how to mix async and non-async code in the same code base in a way that is safe, in a way that is structured. This is also going to go to the docs in FastAPI and async. The full stack FastAPI Postgres project generator, like I haven't been able to update it in a long while, and there's still like a lot of companies and things being built on top of this. This is going to have the latest FastAPI versions, the latest features. It's going to be based on Pydantic version 2. SQL Alchemy is going to be replaced by SQL model. This also means that a lot of the code is going to be super simplified, and it's going to make things much easier because there's quite some complexity in that template that was just made to make type annotations and all these things work. But now, with the latest version of SQL Alchemy adopted a bunch of the tricks from SQL model. It's just like some of the things it just cannot do. For example, like being at the same time a Pydantic model, so still SQL model is, you know, like still a valid option for that. So SQL model will replace that. Vue.js is going to go to React with TypeScript and hooks, some Kubernetes stuff, GitHub Actions, like, you know, a bunch of like the additional things to revamp all this project generator. Now, the future plans for FastAPI itself. So Pydantic is going to be used for serialization and parsing. This is going to improve the performance a lot because all that logic is going to go to the Rust side instead of being in the Python side. So all the JSON parsing and serialization is going to be able to be done in the Rust side through Pydantic. You don't have to do anything for that. It's just going to happen. So a bunch of other performance optimizations for FastAPI. Some refactors for routers. You don't need to understand this, but in case you're curious, this will allow having middleware per routers, having custom routers, like custom router classes, having dependencies per router, including dependencies that could handle 404s. This means that for many cases, you will be able to replace middleware and middleware logic with dependencies in FastAPI. Also, Pydantic models will have support for defining form parameters, query parameters, cookie parameters, headers, like all that stuff. Right now, you can define the types, and you can define a single parameter and say, like, this comes from the query. But you cannot define, hey, this whole model, this whole Pydantic model should be extracted from the query. So it's not as easy to reuse a set of these fields. This is going to also come to FastAPI. Also, a bunch of auth and security tools and documentation, including OAuth 2 with third parties, single sign-on, cookie-based auth, bearer tokens, a bunch of additional things. most of that code, all that code is already there, but it has to be there has to be a lot more documentation explaining how to properly use all these things. Also, a bunch of improved dependency overrides for testing. This is just to make sure that the cleanup is simpler and clearer server errors. This is one of the things that is not necessarily as obvious, but whenever you mess up in your code and there's a server error, it's not an error from the client. It's not that the data is invalid in the client, but your code is invalid. The things that you are returning are actually invalid. The server errors are not as clear as they could be. So it's going to have a lot simpler and more understandable tracebacks with rich and more localized information that can help you figure out where exactly is the problem that you need to fix. Also, docs for liveness and readiness. This is just, just docs, but this is useful for Kubernetes people, and people ask about this. Customization for parsing and serialization, so you can handle things more than just JSON, so you can have a YAML API or an XML API if you like to punish yourself. You can also, there's going to be some refactors of the internal code. So for example, to adopt, for errors, to adopt the standard for defining how the errors are. So this means changing some keywords here and there or things like that. And some code improvements and simplifications that also involve some deprecations and some changes here and there. There's going to be improved lifespan support on the API for interacting with lifespan. Also improved the way that you interact with middleware, so you can have better type annotations and type checks whenever you are passing arguments to the middlewares, to the custom middlewares that you are creating, because right now it's a bit more difficult and you have to remember what were the parameters that you created, but now this is going to have a bit of more, typing black magic underneath. Now, there's going to be NoSQL tutorials and stuff, dependencies, refactor for dependencies, to allow dependencies to end. Whenever you use a dependency with yield, this underneath this uses a context manager. If you don't know that, that doesn't matter. But whenever you use a dependency with yield, you have code that is run before and then code that is run after. Right now, the code that is run after the response is sent. Now, this code is going to be able to run before the response is sent. So after the response is created, but before it is sent, which means that you don't have to wait for all the network to be done before being able to execute that code that is finishing. So this will help with performance, modifying the response before sending it back, and in particular, this will help with connection pools because you won't be holding the connection. For example, a database connection from the pool until the request is sent. You will be able to return that connection before the request is sent after you are done generating the data. And then you're just waiting for the network, but you can let the rest of the code handle the next request using that connection. I also want to play around with this idea that I have been cooking for a while to support batch processing inside of the same process, inside of the same thing, so that you can receive multiple requests and then, for example, generate a machine learning inference for multiple requests at the same time. So you can vectorize that implementation and get all the performance for CPU or GPUs or whatever that you want to do. But this is still, this is just lab stuff, just non-binding things. But anyway, some of the things that I want to work on. This is what I had to show you. Thank you very much. Thank you very much. Now, we are going to go to first, make sure to check the QR code. That is where we are going to do the questions. We are not going to do questions now. We're going to go to the next talk. But if you have questions, please go there. We're going to handle them at the end, after the fireside chat with Armin. Now, we're going to go to the talk by Marcelo. So Marcelo, if you don't know him, wait, I have to present you because you are Marcelo. You might have seen him in GitHub as Cludex, which is not that clear to see as Marcelo. If you have been using FastAPI and you have been asking questions, there's a very high chance that he has been answering your questions. He started contributing to FastAPI and helping a lot with the FastAPI community. And he became currently the official top FastAPI expert. And now he's also the maintainer of Uvicorn and Starlette, which are the tools that are used underneath by FastAPI. He also joined the Pydantic company. So, he's just touching everything at the same time. And he's, been a great help from the community. Also immediately adopting the culture of FastAPI and being super welcome and being super friendly to everyone and just trying to help. So it's amazing to be able to have all his help and to have him here talking a little bit about the history of FastAPI. So please welcome Marcelo with a warm applause.
Yes, hello. I'm going to be talking about the history of FastAPI. But first, well, FastAPI, Sebastian already introduced me, but I have the slides. And I don't have many slides, so I'm going to have to repeat, so I have a bit of more of time. So I am, as Sebastian said, the top FastAPI expert. I've been mainly helping on the community on the GitHub issues on FastAPI for the last 3 years and something. Yeah, and the one next to me is David. He works with me at Pydantic, and he's great. And hold on, I'm not, hold on. This is not connected. Can you see that? Oh, yeah. Aha. Well, yes, yeah. So I'm one of the maintainers of Uvicorn and Starlette. Uvicorn is a web server implementation that runs applications that looks like FastAPI. So if you have an application that implements ASCII, so it's going to run. And Starlette is one of the dependencies of FastAPI. I'm also a maintainer there. And yeah, I've joined Pydantic some month ago. It's been 6 months, and that has been pretty nice. Really like to work there. Yeah, this is just the announcement of the company. And yeah, so today I'm going to talk about the history of FastAPI. It's going to be a bit, it's going to be the history of the framework in kind of sequence of what happened during the last 5 years, almost 5 years, yeah, 4 years and some month. Yeah, so the first I'm going to give a bit of historical context. So at the time we had, when Sebastian was about to create FastAPI, we had 2 main web frameworks that were in the ecosystem that were the most popular ones. One was Django, and the other one comes soon. I just put this slide also as one of the inspirations of FastAPI was Django REST framework, which was created by Tom Christie, which is also the creator of HTTPX, Starlette, Uvicorn, and a lot of MKDocs as well, and other different stuff. Yeah, so yeah. And also Flask. Which was also one of the popular, more popular at the time. And I put this Flask API spec because it was also one of the inspiration to how FastAPI, one of the inspirations for FastAPI. So if you look at it, it was just a bit different. It made use of Marshmallow, which is also another validation library that is worse than, well, it's on my contract. That's kidding. It's an alternative for Pydantic, but I'm not sure if it's maintainer or something nowadays. But yeah, so let's continue. So another inspiration was API Star. The name is correct, right? API Star, yeah. So this one was created by Tom Christie. It is kind of a predecessor, I'd say, I don't know, of FastAPI. It was really, from the beginning, it was, I think, 2018, the beginnings, or something like that. And it looked, well, it gave some ideas, and this is how it looked. If you look at the line 4, you have name, and this is being inferred as a query parameter. Yes. And, well, FastAPI kind of does this as well. And also what it had was the dependency injection. I'm not sure if it was inspired by that or, okay. But it had a dependency injection as well. I was not aware of any other web framework at the time that had this built-in, and API Star did have. This code actually runs, even if you have the pipe there on line 4. This is the version 0.5. If you see the repository right now, it does a different thing. It changed the way it went for, like, the last release. It's not a web framework. It's just another project. But yeah, but this runs. This is on version 0.5. And you can see all the other inspirations for FastAPI on the / alternatives of the documentation. You can see a lot more that's written there besides what I'm saying. Yeah, so let's go to the beginning, the really beginning of the framework. It's been some time already. This is November 2018. This is an issue that Tom created. So Tom, again, is the creator of Starlette. This is an issue on Starlette. And he just created these improvements to schema generator issue, which was, so this schema generator is actually a way to generate the OpenAPI spec, the OpenAPI JSON from the Starlette code. It's not very well known, and it uses the docstring. Yeah, so it still exists and it still works. But then after this comment, well, after this this post, this issue, Sebastian, this is the first reply, where Sebastian, well, he says that, you can see, I love Starlette, and then some other stuff, but pretty much he says, here are my plans, and then after what you see right now, here's what I want to build is the list of features that were being planned for FastAPI. I didn't put it because there's a huge list, but if you see this issue, 172 in Starlette, you're gonna see all the ideas that were being thought for FastAPI. This is November 4th, 2018, and well. At the time, this is just to give a bit of more context, Sebastian helped on contributions to Starlette. So there were a bunch of, I just put some random contributions here, but just to give context, like Sebastian helped a bit on Starlette and also on the Pydantic side. If you see this, the JSON schema update refactor augment, the one at the bottom, is the JSON schema generation, right? So which was fundamental, like for FastAPI itself. So that's, yeah. And this is the first commit, so 1 month later, after that, that issue on Starlette. I don't think this is the official date. I think the official date is 25? 25? Yeah, 24. But this is the first commit of FastAPI. It's been almost 5 years. You can still look at it. Just have the FastAPI directory. And so we were in end of 2018. Now this is almost a year later. This is the release of V1 of Pydantic. So we are already on V2. But yeah, so I actually found out the other day about this, the history, like the timeline, because I actually started using it after this time. And it's interesting that there were a couple of features that were introduced in V1 and were not before. So I found, like, for me that it have been used for 3.5 years and I didn't know about this was just fun to know. Like the root validator were not there. Well, it's said here, I didn't check it, but it was not there before the V1. And other features that were also listed here, like the URL parsing, which I used a lot, and some performance improvements and other stuff. Yeah, so historically, we've been, the release of Pydantic V1 was the end of 2019. And I found about FastAPI on the beginning of 2020 when I moved to France. So that's why you see the tower. I actually got the question of, my boss actually asked to choose the web framework. And he asked me, so you need to choose between Flask and Django, and this was the time that I just started looking for, well, I actually did a pros and cons table and stuff, and I found out about FastAPI at the time. It was May of 2020, and it had 13,000 of GitHub stars at the time, so 5 times less than today, more or less. Yeah, so this is May 2020. This was my first issue on FastAPI, which was actually a bug. At the time, the issues were starting to grow, and this was actually a useful issue, so I was pretty happy that it was recognized as a bug. And also what happened at the end of that year, 2020, was the FastAPI got the FastAPI debug on VS Code, so if you just do that, which was also pretty nice, because all the other web frameworks that were more popular already had that, so just add that. And then on 2021, I joined Encode as well. So there are many projects. I just joined by, so if you join one of the projects, like if you join the organization, you are kind of maintainer of all of those packages, but I was only helping on Uvicorn itself. So this is just the graph of the help that I've been doing commit-wise. But yeah, but the thing is, this is the first step that I took for kind of starting there on Uvicorn, which was just creating an issue that I just want to help to add type hint on the project. It didn't have. So I kind of didn't understand the code source for a long time. I think more than a year I was just adding type hints and not understanding properly what was happening. At some point I started learning stuff, but it took a lot of time. This issue took 2 years to be completely closed. So I'm pretty happy that we closed it. But it took a long time. Yeah, and then after starting with with Uvicorn, I started with the Starlette because Jamie, one of the maintainers of Starlette at the time, which no one knows, I guess, but he was helping a lot at the time, and he was the one that merged the NEIO request. So nowadays, FastAPI supports you can run with Trio as well. And that's pretty much because of Jamie merged that. Well, a lot of help from Alex, the NEIO guy, and Thomas Granger as well. But it was everybody working together on that stuff. Yeah, and then after I start, so yeah, the thing is, Jamie stopped helping for some reason that we are not aware. And then when he stopped, I just joined a bit, and then I started helping as well. And yeah, as I said, we got the NEIO support at the same time. So this is mid of 2021. It's been 2 years and something. And I started helping after this release. So almost all the releases after this, I did the release. Yeah. Oh yeah, and then in 2022, so we were in mid 2021. In 2022, I moved to the Netherlands. Great country, I really recommend. And I felt so, I mean, I'm saying this because it also changed how I worked on open source, because I was more happy on my life. So I actually had a routine on open source. So it really helped on, well, maybe no one's interested about this, but it really helped on open source as well. And yeah, you didn't took this slide from me, but you took the other one. So this one is just, this is end of 2022, which just shows that FastAPI has passed Django in downloads. And I just put it here because we are on the timeline, so this is pretty cool. And yeah, and the beginning of 2023, hey boss, which Pydantic got an investment from Sequoia, and the company was born. So that was pretty nice. And Sebastian also got help from the open source fellowship from Sequoia as well, and he was able to work this whole year on open source. So that was pretty nice, since it kind of creates a new way of working on open source, like an innovative way to spend the full time on this activity. And some month ago, the Pydantic v2 was released, which I'm pretty happy. And Samuel is going to talk a bit more about that soon, so I didn't put any detail here, but yeah. And this is the slide that you stole from me. So I don't have much to talk about it. It's just Sebastian already talked about it. Yeah. And what about the future? From my side, well, you said about FastAPI. From the side of Starlette and Uvicorn, well, the idea of Starlette is it's already stable. In theory, it's already possible to do the V1 release. From the side of Uvicorn, there is a lot of stuff that I want to get in before that, so not anytime soon. There is a lot of improvements to be made for logging that people complain a lot. I complain a lot as well. Workers, not depending on Unicorn for the process management as well, and all small features are a bit bigger, but yeah, that's pretty much the thoughts that I have, and that's it. Thank you.
Thank you very much. Now we're gonna have Armin himself. I still can't believe it, you know, like the creator of Flask is here. God damn it. Like the people from Sentry told me, hey, we want to organize this meetup. It's going to be a little bit bigger than a meetup, a little bit smaller than a full conference. And they're like, yeah, well, like, you know, like I have a bunch of things to do. And like, we're going to bring the creator of Flask. I'm in. Let's do this. This is just so cool. Like, you know, like I started doing Python, working with Flask. I learned to build web apps and things with Flask. FastAPI got a lot of inspiration from Flask. So, you know, like for me, it's just like just such a huge honor to be able to introduce you to the great, I always say Armin Ronacher, but it's actually Armin Ronacher, and it's like, you know, German. Please give a very big applause to Armin Ronacher.
Hello. It's actually quite nice to be here because I mean I think at this point probably a lot of you know that I built a Python web framework, but also I kind of left Python for a while to go to other grasses, Rust in particular, and I'm actually super happy that FastAPI exists because in many ways I didn't know how to continue Flask, and this is really good sort of new generation of framework that came out. So I want to talk a little bit about some of my other passion, which is Rust. So what you have to know is that I work at Sentry, which is also throwing this thing here, in Vienna, which is quite close. And I started there, I think, 9 years ago. And one of my first courses of action was to bring this language, Rust, which I really like, into our Python code base. And I think it worked out really well, and I want to share a little bit of what has happened in the last 9 years with Python and Rust, because it turns out Rust is kind of slowly creeping into the Python ecosystem, and I think it's quite exciting, and I think there's a lot to learn from it. I used to say that I love Python. I've changed my opinion slightly. I appreciate Python. There's a difference in it. I think it's an excellent language for solving problems, and I think it is still an excellent language for solving problems. Maybe not every feature in the language is one that I really like, but when I have a problem, I pull out Python or Rust. But like I usually pull out Python because like most of my problems are small scale, and it works really well for that. It has an awesome ecosystem, and I think it's still getting much better. And quite frankly, it's still a really good language to build a business on top. And I see this a lot because like I'm around for a while, and so people try to pitch all of their ideas to me. And a lot of the ideas that people pitch on, to me at least, are built on Python, which is really nice. But I also think that Python is a very duct-tapey language. It's I would make the argument that maybe it was once pretty, but it's no longer pretty. I think type annotations might have contributed to this a little bit. But it's also not necessarily pretty because it's a very leaky abstraction over the interpreter. There was a time, and that's probably at least more than 5 years ago, when alternative Python implementations were quite popular, and I don't think they are anymore. Iron Python is very dead. Python is pretty dead. PyPy is not dead, but it's not nearly as popular as it used to be. And so this puts us back into a world that was there maybe more than 10 years ago, where people went pretty deep on CPython internals. And because this language is kind of leaky through CPython, it is actually, in practical terms, very pragmatic, because it means that you can actually just fully go in on this interpreter and extend it to your heart's content with C extensions, or nowadays Rust extensions. And this is really pragmatic, because it means that if you have a problem that maybe Python is not particularly great at because you need performance or something like this, or concurrency, you can go a level deeper and play with the interpreter internals. And Python has something which I think is underappreciated, which is it's very, very, very predictable. It doesn't have a cheat, so it doesn't require a bunch of time to start up and be fast. Maybe it's not the fastest, but it's fast enough, and it has really awesome memory performance because it doesn't require a garbage collector for most of the stuff that it does because it's reference counting based. So unless you build massive uncollectible cycle of graphs of objects, most of your memory goes away the moment it's no longer used. And this means that for the most part, Python software at scale in the web space just works. No tweaking of the garbage collector or anything like this. Maybe that doesn't translate that well to like desktop environments, but at least on the server, it's really, really good. And it inherits, or Rust has a very similar runtime behavior because you also rely on garbage collection, sorry, you rely on reference counting as garbage collection. So they have a little bit in common. And I will make the argument that Rust is right now actively changing Python. And I want to show a little bit of why this is the case, I think. This, I made a tweet the other day where I said like Python is not memory safe. And I made it to say like, how controversial is this take? And I think it was very controversial because people didn't like it, so I changed it. It's now called Python isn't particularly memory safe. And so I do Rust a lot, and I think there's a rule in Rust now, which is if you manage to segfault Rust without using unsafe, then it's a security incident. Like it's a security issue, or it's marked as like high priority, this needs fixing. Python gives you a lot of things to shoot yourself into the foot, one of which is called C-types Python API, where you can literally call the internal Python API and do things that you're not supposed to do. Like, for instance, randomly deallocating Python objects, and it will crash. So obviously, this is holding it wrong. You're not supposed to do this. But my point on Python not being particularly memory safe is that there are also APIs in Python that just have bugs for 10 years, and they also crash the interpreter. This is my favorite one. I think it's being fixed. I'm not entirely sure. This is a PR open on this, but for the last 10 years, this crashed Python. What's going on here? There's an API in Python. It's called memory view. It used to be called buffer in the past. You don't really see it here, but this B up there, this argument to read into, this is a Python object that references a buffer that's managed by someone else. So what's going on here? Well, if you take this buffer, which is given to you by the buffered reader, and you leak it out into a global variable, and you hold onto this after your read operation, what's going to happen? Well, short answer is it crashes. So why does it crash? Well, because the IO buffer reader down here is being created. It reads 1 byte. That's enough to put this thing into a global scope. So the global buff assigns this. And for whatever reason, predictably for the last 10 years, if you create a new list with the same size of the buffer that you have internally, it just reuses that allocation. I'm assuming there's a free list or something. I don't know. But what this means is that if you assign to this buffer 0, and then you read the first element of this array, it crashes. So what does it mean? Well, it's a 10-year-old bug on crashing the interpreter with what I would argue is safe Python code. Anyways, my point is that Python has a more of a pragmatic approach to this, which is that, well, you don't write code like this, and so it doesn't crash, right? In Rust, it's a little bit different. Another thing on this is that Python really loves C extensions. And I think Python actually got incredibly popular because of C extensions. It went through different waves of this. I remember a time when people used to write Linux applications in Python. And the big reason for this is that you could actually use PyGTK, PyQt, and stuff like this. When I started using Python for web services, everybody used PIL because bots came to the internet and everybody had his own captcha implementation. And then obviously mod Python was one of the first ways in which we got high performance Python web services going. But then there's the whole scientific Python community, which is entirely based on this idea that you can build optimized matrix multiplication and shit like this in C and not in Python. And then obviously there's like system libraries like OpenSSL that you have to interact with. So Python really has a rich ecosystem and history of writing C extensions. And Python accomplishes this through the global interpreter lock, which there seems to be some movement going on maybe getting rid of it. But this global interpreter lock is really what makes this whole experience remotely safe. You hold this lock or you release this lock, and for as long as you hold the interpreter lock, you're kind of allowed to do almost anything with Python objects. You're just required to put them back into a reasonable state by the time you release it. As a Python programmer, you don't give a shit about this. It's a really fun thing to have as an argument when you drink beer with friends about like why the language is not great, but you don't really see it other than that. But when you write C extensions, you actually do see it, because like you have to deal with this thing all of a sudden. So it's a very core foundation of the C API. This is changing a little bit now because of the multi-interpreter support. I don't know how familiar. Did anyone hear about per sub-interpreter GIL? Raise your hands. Well, it's actually not that many. So this is actually really exciting, because there are sub-interpreters in Python for a really long time. They used to share a GIL. So it didn't matter how many you had, they all shared the same GIL. Now you can have a GIL per sub-interpreter, which is actually pretty significant change. You can't do much with it yet, because it's not really that well exposed. But in theory, you can build actor frameworks or stuff like this that are using message passing, and you can saturate every core, and every core runs one interpreter. That's the idea. It could be amazing. And I mean this without joking. I think this could actually be a pretty significant change in how we use Python. But this is actually changing for the first time, I think, some of the underlying guarantees that the GIL gives you. Why does this matter? Well, I think it matters because what happened in the last couple of years is that people realized C is not a lot of fun to write. And so if you wanted to write extensions for Python, C was the language to go for. And so Rust creeped in. We do this at Sentry quite a bit, but a lot of other people did too, including the cryptography library is written in Rust. Pydantic recently got a lot of Rust into it. If you have spent any time in the fancy-pantsy AI ecosystem in the last couple of months, actually only, there's a lot of Python Rust code appearing. So that it is happening, right? It's like, it's at now mission critical. Like Rust, Python has to work. Like you can't, like, if Python would change in a way where the Rust ecosystem, Python ecosystem would no longer work, it would be a problem, right? It's it's critical now. So, why is Rust popular for Python? I think it's actually down to these two things. Py03, which is a binding of Rust to Python and the other way around. So you can either embed a Python interpreter into a Rust program, or you can compile Rust code into an extension module for Python. And it comes with this tool, which I don't know how to pronounce, Maturin, I don't know, that just is a developer experience utility that helps you build this thing. And this just makes code really easy to write and shockingly fun. You just run Maturin develop in your Rust crate, and it spits out a Python module that you can import, and it puts it into your virtual env. There's a little command you have to run first to create this project, but it's that simple. It's like you keep running this, and you just have a running wheel that you can use. So it takes away a lot of the handcrafting code that you had to do originally. Like Sentry's use of Rust is not nearly as convenient just because it's 10 years old. And I don't want to bore you with a bunch of Rust code, but the whole idea is you basically put a bunch of annotations on top of your Rust structs, and magically they appear as Python objects in your extension module. So if you have, for instance, this is, I have an implementation of Jinja for Rust, which is called mini Jinja, and it's just a Rust crate. It follows, it knew nothing about Python. It just follows best practices in Rust. And the entire code that exposes this library to Python is, I think, less than 150 lines long. It just wraps every single thing in this Py class and Py methods, and it just works. And the reason it works, and you can also have properties and stuff like this, and the reason it works is because, as I mentioned earlier, maybe Python doesn't care that much about memory safety as Rust does, but Rust really cares about memory safety. And Rust has, I don't know if you're familiar with this, but it has a thing called the borrow checker. It's a little bit of a running joke because Rust is maybe not particularly nice to use because the borrow checker says no all the time. And the borrow checker really tells you just one thing, which is only one person at a time is allowed to observe a mutable thing, but everybody is allowed to observe immutable things. So if you see something that's immutable, you guarantee that nobody else is allowed to mutate it at this time, which is a guarantee that Python has never ever given you. Python didn't care about Rust for good reason, because it didn't exist, and the Python C ABI doesn't uphold this guarantee at all. So how does PyO3 work with this? So it basically has this idea that you can acquire the global interpreter lock during a function call. So when you call Python with GIL, it holds the global interpreter lock, and while it's holding on to this thing, you can execute Python code, you can do a bunch of stuff, and you can interact with Python objects in the Rust side, and the Rust borrow checker sort of guarantees that everything that you're doing is safe and sound, because it will basically do two things. It will acquire the global interpreter lock for the duration of this block, and it also holds on to a little bit of memory pool. It's a little bit of area of memory into which you can put temporary objects. So if you, for instance, call this, I mean, the only thing that really matters here is like py.eval says like, please evaluate this Python code to me and give me the result back. And so in this case, it just allocates a new string called hello world, and it returns it. And this py string is a reference to this temporarily held memory. And so for as long as you're in this block, you can do whatever you want with it. When the block ends, then it will deallocate the memory that's still there, or gives it back to the garbage collector. In any case, it makes this working with the GIL explicit, and by Rust standard, it makes it safe. And it relies on this idea that while you're holding onto the GIL, nobody else is fucking around with your Python objects, which so far was true. Now, it's not necessarily going to be true going forward because of multi-interpreter support or because of GIL-less Python. But so far, present-day Python, this is working. And it's working well, and we built a lot of infrastructure on top of this now. So this is just recapturing this. This works because we can hold on to the GIL, and we have a place to put temporary memory allocations. And this is, I think, the point of this presentation, which is there's an alternative world where we wouldn't have given a shit about Rust at all. Nobody would have picked it up in the Python ecosystem, and we would have a bunch of work happening now, like multi-interpreter support or getting rid of the GIL. And that would happen in the Python ecosystem only. But now what happened is that we built a bunch of mission-critical software. I mean, it's maybe not mission-critical, but we built a bunch of really interesting software in the Python ecosystem on top of Rust. And all of a sudden, Python cannot change a bunch of random things with it also considering that there is a Rust ecosystem built on top of it that also has to continue working. And so now, when GIL goes away, or when the multi-interpreter support comes in, people are actually engaging with the Rust community from core Python in one form or another, trying to figure out like how do we bring these two worlds together. And I think this is really fascinating. I don't know if it will necessarily mean that Python will change a little bit to accommodate Rust better. It's unclear. But if you look into the pull requests on the PyO3 support for no GIL, which gets rid of the GIL, or the PyO3 discussion about how to bring multi-interpreter support into it, none of these things would have happened if we as a community wouldn't have picked up on a critical mass level Rust as an extension module to Python. And now sort of two communities need to work together somehow to figure out how to make this whole thing a little bit safer. And I think that's a pretty interesting outcome that I honestly wouldn't have expected a couple of years ago. And this is, I think, overall most likely going to result in better outcomes for both Rust and Python. Yeah, and that's all I can tell you about this part. And if you have questions on it, just submit to this QR code, and we will go over it later in the fireside chat.
Thank you very much, Armin. That was so cool and so sophisticated. Yeah, so exciting to be here. Now, next, I'm going to tell you, like, when I was starting with FastAPI and all this stuff, I was like, okay, I need something to validate data and stuff. And, like, there are some libraries and some things that I have tried. But then there was this library kind of hidden somewhere that was being able to do data validation, serialization, all this stuff just from type annotations. And I remember seeing that and being like, well, this cannot work. I'm missing a piece of code where you import some Pydantic string or something. And no, it just did work. And that was when I said, like, I want to build this thing, but it has to be built on top of Pydantic. Nothing else is building it with Pydantic, but like this is just doing this is doing the thing that I want, and I don't know how it does it. When I started helping a little bit with tiny pieces of Pydantic, I saw that was the most complex code that I had ever seen. It had to use some of the internal stuff from Python that is not even documented to be able to extract and do all that logic and all that stuff to be able to expose a very nice user interface for developers using Pydantic, and then dealing with all the complexity necessary underneath. And now we have all that complexity and all that stuff is being done in Rust, which is a massive improvement in performance and correctness and all that stuff. So it's great to be able to have the author of Pydantic, Samuel Colvin here. When I say that FastAPI is standing in the shoulders of giants, I didn't know that it was actually true. They were actual giants. So please give a warm welcome with a big applause to Samuel Colvin. Thank you.
I've got this one. You take that one. Thank you so much. So, first of all, is it not working? Can you hear me at the back? It's okay? Okay. So just before we go any further, how many people thought we were all mispronouncing Pydantic for the first half of this talk? How many people hadn't heard about Pydantic before today? Okay, good. So most of you have some idea about what Pydantic is, so I will skip over the intro, but yeah. Pydantic does data validation and serialization using type hints. It's now very widely used. We just hit 1 billion downloads last week. We're downloaded about 95 million times a month. So although FastAPI is one of the ways that Pydantic is best known, and I think is how lots of people first come to Pydantic, it's used in a whole myriad of different contexts, both in other web applications and in lots of contexts where you need to basically interact with real-world data from Python that isn't a web interface. There's a small example of Pydantic, but given that you've all met it before, I will go on to some hopefully more interesting things. So Pydantic v2. Come to, what year are we now? Beginning of last year. God, it feels like longer. Beginning of 2022, Pydantic had all this usage, but I was not particularly proud of what was on the inside, and I kind of thought there was a world in which maybe we could make Pydantic slightly faster. And I started this experiment in a file in Rust to see if you could basically use Rust code to do some validation of Python objects. I went into a kind of hole for about a week and came out with something that I thought was going to be the next version of Pydantic in a couple of months. Fast forward a year and a half, starting a company, lots of other things happening, and we actually have Pydantic v2 now. It was released back in June, year and a quarter after I started work on it. And so yeah, it's a complete rewrite of Pydantic. All that has really remained unchanged is the unit tests, and all of the core is written in Rust and gives us this 5 to 50 times speed up over Pydantic v1. And that's not the end. We're going to carry on getting faster, and I'll explain why. But along the way, we've also added more features and become more correct. So yeah, a massive change. Why Rust? Apart from my sort of interest in using Rust, why is it actually a good idea? There are a bunch of reasonably obvious things that make Rust an attractive tool for something like this. Obviously, performance is number one. The reuse of high-quality libraries. We, for example, use the URL validation library that Mozilla built when they were building that web server that died in the end. What was it called? I can't remember. But it's a very high-quality URL validation library written in Rust. Not that there aren't in Python as well, but they're faster. And most of all, more explicit error handling. So I haven't got examples of Rust code here, but you're effectively, you have something that feels like type hints, but for exceptions. In Python, one of the things you don't know anything about is when you call some code, what exceptions might it raise? And there is no way at the moment, no database of what exceptions might get raised, no willingness from the Python community, as far as I've heard, to have that in Python. But when you're writing code like Pydantic, it's incredibly important. So whereas in Rust, you are forced methodically to cope with every type of error, which is very useful. Then there are some perhaps less obvious advantages to doing Rust. And one of the big ones for us is this idea of zero or minimal cost customization, that you can put in user switches different bits of behavior, and because that if clause effectively is being run in Rust, you pay real world effectively zero cost for doing that, whereas if it was in Python, that would start to add up. It's arguably easier to maintain. I mean, those of you who are happier writing Python wouldn't agree, but it'll tell you about a bunch of errors that you would never get told about in Python. And another thing, which is both an advantage and a disadvantage again, is that private means private. If you don't export something, there's no way someone can go and find it, import it into their code, and then rely on it, and then be furious when you take it away. That we have mitigated quite a lot in Pydantic v2, where we put underscores everywhere in an attempt to stop people importing stuff that we thought was private, but like obviously in Rust, you can actually make things genuinely unavailable. And there are some disadvantages that we should definitely admit are there as well. It's slower to develop, there are fewer people to help you, and there is this whole work of distributing, building, I think we build like 60-something binaries for Pydantic to try and cover as many people as possible who might download it. I think we have like, I think I calculated from about 250 million downloads that we cover 99.59% of people, but there is someone who is using, what's that, there's a Windows environment called where you can't get binaries, that there are some very edge contexts where binaries aren't available, where that can be difficult. So how does it work? Sebastian was slightly wrong in saying that all of the magic is in Rust. All of our code to basically read the type annotations in your code is still written in Python. And what that effectively does is reads the annotations, builds this big dictionary, which is effectively a definition of your schema. It's somewhat like JSON schema, but different because we have to include lots more information. We pass that to Pydantic core, where we have this JSON schema class that we initialize in Rust and return. So it's available as a Python object, although it's implemented in Rust. And that is stored on a Pydantic model. And then when we come to do validation, we effectively just call the method on the schema validator. All the validation happens in Rust. And you call back, you return that into the Python world. One of the other things that we're able to do, which isn't included in this diagram, but is quite important, is that while running validation in Rust, we can call Python code, including your Python code. So you can, when on a Pydantic model, you implement a validator. That is stored as a reference inside the Rust schema validator and gets called during validation. And indeed, lots of the validator types that aren't that commonly used, like a DQ, for example, a DEC, sorry, that's implemented in Python because we just haven't gone to the length of implementing all of them in Rust yet. So, some examples of Pydantic v2. I gave a similar talk back earlier in the year before Pydantic v2 was released. So, hopefully lots of this won't be as new to some of you, but first of all, performance was obviously the headline change in Pydantic v2. We have a very simple Pydantic model here with 4 fields. This code runs unchanged with Pydantic v1 or v2, and sure enough, you go and run it, and you get a 22 times speed up for just upgrading the version of a library. That's not 22% or 2x, that's 22x speed up just by up-revving the library, which is massive. I don't think any other library has done this bigger rebuild post v1 in the Python ecosystem that I can think of. Strict mode is something people wanted in Pydantic from a long way back. When I was first using Pydantic, it was in context a bit like it's used in FastAPI for validating HTTP headers, things like that, where you knew the input was a string and you wanted the Pydantic v1's behavior and Pydantic v2's default behavior of basically lax coercion, trying desperately to give you the value that it thinks you want. But there are definitely cases where that's not what you want. So here, we set the config to say this is now a strict model. We add, here we've got 2 fields, one's an integer, one is a tuple of two integers, and then we pass to it data that would be valid if we were not in strict mode. Pydantic would take care of coercing the number 42 into the string 42 into 42, and the list that contains 1, 2 into a tuple, but in strict mode, it won't do that. Now, strict mode isn't actually that useful in the real world because very often the place where the data is coming from doesn't have the same rich set of types as Python does. So for example, JSON has some of the primitive, 7 types cover some of the primitive things like integers, lists or arrays, but it doesn't cover lots of other things like tuples, like dates, where you might say the date is strictly correct in JSON, but actually, as far as Python's concerned, it's a string. So strict mode is only really very useful if you can also run, as we do here, run the validation of your input data directly within Pydantic. So this is something that wouldn't have been possible when Pydantic was written in Python, because we would have had an incredible slowdown if we had done all of our JSON parsing in pure Python. But instead, we're able to use, at the moment, the serde library and soon our own, to do the JSON parsing as we're doing the validation, and therefore make clever observations like, while it's an array, we want the input to be a tuple, but we know that in JSON, an array is the nearest we'll ever get. And similarly, if you had, say, a date, that would, Pydantic would take care of coercing the date string into a date object, whereas if the input was Python, obviously a string is not strictly correct, doesn't strictly match the date type, and so it would give an error. So yeah, we get big performance improvement because we don't have to construct Python types, then do validation, then return new Python types. We can go straight from Rust types into Python. Custom errors for types where it makes sense. We can talk about arrays instead of lists. And lastly, in future, we should have line numbers as well. So where a validation error has happened, we can say what line of Rust that happened on. I'll talk a bit later about how that will work. Wrap validators are another big functionality improvement in Pydantic v2 that, again, would have been possible in Python, but would have been much harder to implement and would have had a slowdown because you would have been constantly looking at what type of validator you had. And so the idea here is they work a bit like middleware, or a bit like the onion, as people sometimes call it in middleware within web frameworks. As well as getting the raw value as your input to the validator, you get a handler that you get to call whenever you like. And so you can do logic before validation, on error, or after validation. And that covers what used to be 2 different validators and stuff you just couldn't do, like intercepting the error and returning a different thing. Alias paths are another big improvement. They're actually inspired by serde's flatten functionality. So the idea is you have an object with nested values that you want to pull out and put into your top-level Pydantic model. That wasn't possible in Pydantic v1, or you could write your own validators, which worked but was hacky. Now we have alias path, which effectively lets you give a path to the value you want to extract, or alias choices, where we would look for we'll look through different keys to find the value you want. And you can combine alias paths and alias choices into arbitrarily deep, crazy ways of finding the value you want. And so you see here, we extract the 1th element of the list and then the bar value from that. So those are some of the most exciting things that have come in V2, or things I've been most excited about. I'm going to talk a bit about some things that are coming soon, and I'm about to cover go on for exactly what Armin was talking about with Pyo3. So within Pydantic, we're really lucky to have David Hewitt, who is the primary maintainer of Pyo3, working with us. And so this speed up to Pydantic is actually stuff that's coming down the line from Pyo3. So this is really introducing Pyo3 again, which Armin has already done, so I'll go on. But the fundamental point here is that although the Rust code is very fast, the way that Pyo3 interacts with Python objects could become much faster. So here we've got a very simple example of a function we have in the Pydantic core code base that we call a lot, where we basically take a dictionary as keyword arguments and we return it, but with the none values removed. And you can see here 4 different ways of calling that. Pure Python takes 280 nanoseconds. So all of these things are very fast, is the first thing to say. And the thing that you wouldn't expect to hear in a talk about Rust is that the Rust is actually slower than the Python. And the reason for that is twofold. One, that Python code is actually pretty well optimized. There's it's almost all fast instructions. There's a particular fast instruction for if value is not none. The Python code is already pretty fast. And the Rust is effectively, in the naive case, only able to do about as well as Python. But there is a slowdown, which comes from the fact that effectively Rust has this concept of lifetimes, where you have to be very specific about how long you think a variable is going to exist for. Python absolves all that away from you and doesn't give you those lifetimes. That becomes a problem when you're interfacing between Python and Rust. And the way that the guy who first built Pyo3 got around that was he basically had a vector, a list, where he allocated every pointer to every Python object that he created into that vector. It gets around the problem really elegantly, but it means that every time you want to construct something or take in an argument, you need to allocate into this vector, which is slow. So in the case of the Rust, you can imagine if you wrote this out not as a comprehension, you would say output is a new dict, and then we're going to iterate over quargs and add things into new dict and then return it. Constructing that new dictionary involves allocating to the vector. Constructing the dictionary, which is quargs, is also allocating to that vector. And so you have that overhead on top of effectively the same code as Python, hence why Pyo3 today is slower. So the next thing that Pyo3 is going to do is remove that vector effectively, and you're no longer going to have in the Rust code every Python object having the same lifetime. And then there will be a compatibility layer that basically reverts that behavior for a while. And then, so to be clear, the bare metal FFI you see here, which is much faster, it's still written in Rust today, still uses Pyo3, but it's basically a massive blob of unsafe. And particularly, the reason it is able to be much faster is it's able to use the keyword arguments without constructing the dictionary that you would see them as in Python or in normal Pyo3 code today. So someone in the room is going to correct me when I describe this, but I think you get 3 arguments, which are the number of arguments, I forget exactly, but effectively you get a list of tuples of the values within the dictionary when you call a C function, or indeed a Rust function with quargs. And if you can run this code without having to construct that first dictionary, everything's much faster. And that's where the bare metal FFI gets the big speed up from. And again, it should be perfectly possible in Pyo3 in time to give some nice, safe abstraction over that construct so that you could say, I want quargs as an iterator rather than as a dictionary, and you would get that. The other big change coming down the line, and I should say, just on the performance there, we should be getting the next Pyo3 without allocating to this vector later this year, and that should, we think, roughly give us a 25% speed up. So on top of that, 22 times whatever 25% on top of that means. And then, yeah, further improvements down the line, like this idea of having the option to iterate over quargs. And then the other big change we want to do is we want to remove our current JSON parsing. So what we're effectively doing now, and this is, what I'm doing here is pseudocode, which is Python trying to explain some very complex Rust code. This may be an unmitigated disaster, but we're going to try and see what happens. So the idea of what we do now is effectively we parse the JSON as one big step. We iterate over the whole of the JSON, and we build some massive JSON blob, which involves allocating to the heap loads. Once we finish doing that, we go and we iterate over, in the case of a model, for example, we iterate over the fields we're expecting to see, and we get the appropriate keys out of that dictionary and then build our model data. Then we can construct the model, then we can return it. This is efficient. It's what Pydantic v1 did effectively in Python. It's what Pydantic v2 does in Rust. And it's what most of the other similar libraries do. But particularly in the case of parsing JSON directly, we can do something much faster. So the idea here is that we iterate over the JSON, and we effectively we do the validation as we iterate over the JSON. And this gives us massive improvement in memory theoretically, and also a big performance speed up. So effectively, when we get a JSON key, we then look up the fields. We don't have to construct a new dictionary. We've already got that one built before, or that map. And then we can put that value, once we've got it, into a temporary vector. And then we iterate over that vector. If there are none values in it, we know we haven't found a value. We can create a missing error. And otherwise, we can return the data. So the full extension of this won't come until Pydantic v3, where basically the base model for base model will be written in Rust, and where we can do lots of improvements to the performance. But we should get some of the speed up from this better JSON parsing in the next few months. And those changes should all come with, any change before v3 should come with zero breaking changes. And if and when there's v3, I promise you it won't be anything like as broken as the change between v1 and v2. That was fixing the API, and won't happen again. So that's all I've got. Thank you very much. I'll just say one more thing, which is, as you heard earlier, Pydantic is now a company. Don't worry, Pydantic open source will remain MIT licensed and free for you to use, and we're going to carry on working on it. But we are building tools and services for effectively the same people for all of you, and we should have a private beta of what we're building later this year. So either come and find me or take a picture of that QR code and get on the beta list and get a discount. Thank you. Thank you very much.
Can you hear me? Yeah, now you can hear me. Nice. Thank you very much, Samuel. That was awesome, as always. So now we are going to have a short break of 20 minutes or so. So we're going to see each other at 7:40. Before that, make sure maybe we can switch to the QR code for the slide.io. Make sure to scan the QR code. Well, this is not the QR code, but you will see it in a second. Scan the QR code for asking questions, but also make sure to upvote the questions that you care about, because of course we're not going to be able to handle all the questions that are there. But if you upvote the questions that you care about, then we're going to be able to just make sure that we answer the things that are important. Can we switch the slide to the one with the QR so people can just sign into the? Okay, cool. I think we're going to do it in a bit. Yeah. Oh, when you come back. Okay, cool. So when you come back at 7:40, there's going to be the QR code, so you can scan it, and then we can do it from there. Thank you very much. The other thing is the slides are going to be available after the presentation. We're going to publish them later, but yeah, that will be after. So see you on the drinks and snacks, and see you in 20 minutes back here. Thank you very much.